Hello again, still in Barcelona. And who are you?
Hi, I'm Guillermo.
Guillermo, and yeah, okay, what do you do here?
Okay, so I first let's define here.
Okay,
Here
yeah.
is the Barcelona Supercomputing Center, and as the name states, it's a supercomputing facility based in Barcelona, and it's basically a research institution owned by the governments, and it hosts a supercomputer, a very big computer, which is called Mare Nostrum, and also a lot of scientists and researchers who do research here. Most of them using, of course, the supercomputer. What I do in this here is I work in data visualization. And I have a small team of 2 people, and we mostly devote our time to developing narrative visualizations of the results of computer simulations from scientific research.
And what is your background then? Are you a scientist?
So no, I am an artist. I studied a bachelor in fine arts. After that, I studied computer animation, and then I started working in the animation industry, in TV and advertisement a bit, also some video games a bit, and a lot of freelances, of course. And at one point, I was just by pure chance, I think, a friend of a friend was starting a visualization group in this center 12 years ago, and they called me because I was apparently not doing anything better at the moment. And I made an interview, and they hired me, and I started. We actually kind of started together figuring out what we could do in terms of visualization for, simulation results.
Mhm.
So my background is in art and animation. But the good thing is that I still use the same tools and techniques for doing the visualization videos.
When it comes to transitioning from your, let's call it, previous life into this more research-based, more scientific life, what are the most obvious changes, and how did you perceive that transition for yourself?
Well, it was so I can tell an anecdote of to illustrate this. At the beginning, the first year, the first project I did was this together with Fernando, my colleague here. We made this video about the research to build a simulator of the human heart.
Mhm.
So a computer simulation resolving the equations that have to do with the physics of how the heart moves. It was a project in an early stage back then, and we made a video with the results of those simulations, and also some infographics and so on to show this project, to illustrate and explain how that worked. And that video resulted to work very well, and we sent it to some visualization contests, and it won some of those. And so let's say we started to get known in the BSc for doing this job. And at one we had some annual dinner of all the department. And so I didn't understand the jokes. The jokes of the scientists had, words that Coriolis things. So I couldn't understand that. On the other hand, when they walked behind my screen, they saw always very nice stuff, realistic renderings. So they saw the shape of the numbers they worked with, something like that. And so this is to say that it took some translating into what I was doing before, and also to make them accustomed to what I was doing. For me, it started very like, how to say it, very from the base. I started reading papers, for instance, which I didn't do before. So I had to, in order to make these films, I had to start understanding a bit of the science behind the projects.
So you read the papers of the people whose simulations we're working on, or
Yes. And also that led me to the state of the art, or to other papers from other people from the references.
How easy, or how did you find that coming from an arts background, reading those, I imagine,
Very
technically
difficult,
papers?
challenging.
Did you have help, or how did you progress with
Yes,
that?
I always had help here to guide me, but at some point I was left alone to fly on your own. But there is one part that you can understand, and there is the, let's say, the math or the physics that if you don't study that, then that's more difficult. At the beginning, I was staying at the, let's say, more shallow part of the concepts, and because that was enough to illustrate the research project in our videos.
And so the first project you worked on were biomedical, then biomedical.
Yes,
radiation, okay.
exactly.
Let's go a bit into the tools and maybe your history of coming into the job. So before, you've been working in computer animation. What did you use back then?
The first software I learned, which is like my software, in 3D, 3D artists have this thing of, this is my tool. It was Maya.
Okay.
When it was Alias, I think. So I started with that. But after graduating from this master's, I started working with Motion Builder. I was doing some real-time animation for TV shows, on direct, which was kind of really, really fun, but also very stressful because you could just click on the wrong key and everything's wrong. But that was fun. So then in the middle of that, I also had to work with 3ds Max in parallel. So I was learning a lot of tools, but Maya stayed my main software for a long while. Then when I joined the BSc here, when I entered this company, we started working with Blender. Blender is very popular in science because it's open source and you can open it and do whatever you want more freely, perhaps, than with other software. And also it's non-commercial, let's say. It's free. So I started with that, but at the moment, coming from Maya, I felt like I couldn't do what I could. Not to say that Blender is not enough. It's not good. It's a fantastic software. It was just my training was not enough at the moment. So I convinced my boss to change to Maya, which was lazy on my part, but we stayed with Maya for a while, until a moment in which we started developing, because the problem we faced at one point is that there is no pipeline already built to connect the two words we were working with, to connect scientific formats and VFX or CGI. So we started developing our own proprietary tools to convert data from scientific formats so they can be ingested in Maya, Blender, or whatever. And at that point, we found it more difficult to do that for Maya. And also, we found some limitations in terms of how you can manipulate data inside Maya. So we decided to change all our pipeline to Houdini. And we are working with Houdini for 5 years now.
Okay. Did you find the transition easy, hard?
Very easy. But also because we were at that moment we expanded. We hired a new guy in our team, and he was a Houdini. He is a Houdini artist.
Okay, understood.
So it was easier because I could learn from him, basically.
So what's the main difference now that you're working in this tool from your previous tools? What do you think? What in your day-to-day work? What makes the difference?
So for me, it's more the way in which you visualize the data that you are ingesting and you're manipulating inside Houdini is much more. It's much easier. It's much more clear. So you can inspect it and see exactly what you might be doing wrong or where the problems might be.
With you as an art background, would you recommend students to get into this field?
Yeah, absolutely. I mean, there is one part of working with the VFX tools, of course, and making these videos, but data visualization is a research area on its own, and it has so many areas or many paths you can research about. And I think it's becoming more and more popular because there's data everywhere and we need to make sense of it and so on. So the strategies for visualizing the data, making sense of it with, let's say, human capabilities, are also needed, are also necessary now. So I would, yeah.
What do you think are the main skills needed for students to excel in that field?
I'm not sure. I teach data visualization in the university to data engineers in third year. And with basic skills in data manipulation and analysis, you can already, because it's a transversal field, and there are some things that are kind of intuitive if you want. There's also many false friends, but it's something you can learn without a lot of a specific background, because I've also taught data visualization to non-engineers and to artists, for instance. And the principles behind it can be taught, let's say, independently of the tool you use, of the tools you use.
What are those principles? Teach me.
Okay. Some of them have to do with human perception, for instance. Okay. An interesting field in data visualization has to do with how we humans perceive things. So you can exploit those perceptive aspects. You can exploit them to build better visualizations. Visualizations at the end are regarded as devices to help us reason about something. So to guide reason, you can use a certain set of colors or shapes or composition and things like that in order to guide reasoning thinking about a problem, whatever it might be. That's one part.
What's the other?
Oh, no, so there are many. Let me see. What else? You can teach some basic stats, for instance, also to non-mathematicians, right?
Teach me. No. What's the most important thing that a non-mathematician, a person coming from arts, should know about statistics? The single one thing, of course, that exists.
No, the basic descriptive statistics or something like that.
Like a median or a mean?
Yeah, exactly, things like that, but also not aggregating. One thing that you can do in visualization is visualize the whole thing, right? And there is this famous Anscombe quartet. So it's a set of distributions with, I don't remember, a number of points, data points in X and Y, for instance. And so if you take the median, I think it's the standard deviation, the summary statistics, you have the same number for all of them.
Okay.
But if you plot them in a scatter plot, you have different shapes. One is a line, one is and there's a variations of this. There's one, the famous one is the Datasaurus. When you plot it, it's a dinosaur, it's a T-Rex. So yeah, you also can learn things like that. And that part is, I think, is easy to grasp from different backgrounds.
Understood. Let's get back to your tool set and your daily workings, maybe. So, I mean, I've asked the people already what's so super about the computer you have there. Let me ask you, are you actually working on the supercomputer, or how does that work?
So the supercomputer is used, probably they told you, but it's used by scientists all over Europe. So the quota we have for our testing and debug and our own project without asking to the committee for a proper project and that is not that much. That said, I could and I have used Mare Nostrum to do some things. For instance, the data we use to make the visualizations is mostly always there.
Okay.
It's stored there. So we have to access Mare Nostrum to take it. And for big data sets, which is something that is happening more often, increasingly more, because simulations are getting better with better resolution. They can be done in fewer times. So we have bigger data sets, and we are starting to analyzing and converting it to the formats that we need in Mare Nostrum. So that part of the pipeline is usually done there and not in our computers, because it's just the data sets are just too big. We have done some rendering.
I was about to ask, and you seriously did that? Because I was thinking this would be too naive a question to ask.
No, we did. And all of my friends in VFX animation, the first thing they ask me is, you do render there?
Yeah,
of course. But it's not obvious. Well, you cannot. It's not easy to install. So it's not meant for rendering the architecture of it. You can. And in one project we have with this agreement with Arnold Render, that they gave us some licenses to do this. We are non-profit, so we do dissemination of science and that. So they gave us, I think to remember, it was 100 licenses, which is not that much, but it's enough. And we put it in Mare Nostrum and render and watch amazed how the renders were done in no time.
Let me ask you a practical question. Not sure if you're allowed to or can answer this, but how does that work when you want to install a render engine on Mare Nostrum?
I can't. I have to ask a support team, which is one of the teams in the BSc, that team in the BSc that makes the machine work. Basically, they maintain it and keep it working, and they also install things for you. So you have to ask for them to install. The thing with renderers and VFX software, especially the commercial ones, is that you need to install a license server, right? And for what I understood in Mare Nostrum, the license the license machine is not fixed; it's virtual. So it's difficult to know where it's going to, when they allocate you hours, where it's going to be. So that was the technical issue. But that's it. Once we convert the data, our tools or our current strategies are to convert the data to formats that we can work with in our computer. So they are smaller or they are fractioned in parts or things like that.
Could you give me an example?
OpenVDB, for instance, compresses the data a lot for volumetric datasets, of course, a lot with respect to the original datasets, which might be ASCIIs or even binaries, but very big ones.
So what's the typical volumetric dataset that you get in there?
We work a lot with a group that makes a simulation of combustion. So they simulate combustion processes for fuels.
Okay.
Basically, they are researching now in new fuels that are efficient, cheap, and also non-contaminant, like hydrogen and things like that. What they give us usually is what happens inside the combustion chamber.
Okay.
They give us a simulation of all the chemical species, yes, that lie around when they enter and sparks the flame. That's volumetric by nature. So what we do is take that data, convert it to OpenVDB, and then visualize it in Houdini. That was kind of a problem just 1 year ago, let's say. Well, not a problem, but the thing that happens is the computational meshes for simulating these things are quite big, in the order of 50 million elements, something like that. So when you convert that to OpenVDB, if you do a regular grid, then you have if you want to preserve the detail of the small things that happen in the flame, you need a very big OpenVDB, right?
Yeah.
And that can take a lot of space, and that can be difficult to load in Houdini and so on. So one thing we have developed recently in this last year is this tool to recognize what happens in the original computational mesh, which is that it is not regular. What they do in order to make it more efficient in simulation is make the computational mesh with more detail, finer, smaller elements where they need it, where interesting things happen, and coarser where not so interesting things happen. So our tool in OpenVDB captures this difference and makes what we call a multi-level VDB.
Okay, and that is a custom tool that you developed here in-house?
Yes.
And that is not publicly available?
But it will.
Oh, amazing.
Yes, we want to finish it so it is production ready. It's not yet. And we would also like to, let's say, publish it somewhere.
Sorry.
No, we want to make it available for everyone, of course.
Let's get a bit into the nitty-gritty. Yeah, I mean, I already asked you for basically your hardware specs at this point. So what's your render engine at this point?
Our render engine is Karma. We are now 100% Houdini.
Karma on the CPU or on the GPU or both?
We use it on GPU.
Okay, wow.
Yes, XPU.
And even with that large data sets, that holds up?
Yes, it renders really quite fast, yeah.
Amazing.
Yes. We have done some tests with 50 million voxels, and it holds up pretty well.
Amazing.
Yeah.
And so what's what's the span of a typical project? I mean, I come from commercials mainly, so project durations I'm used to are somewhere between 4 to 16 weeks realistically.
Okay. I'm not sure. Okay, so our movies are 5 minutes long.
Oh wow!
But we are more or less 3 to 5. We are small teams. That means we do everything from the script to the storyboard to all the processes except for sound, which we usually outsource. But so production-wise, let's say once everything's ready and convert data and do all the VFX 3D part, that would be around less 8 weeks, something like that.
Wow.
A couple of months, depending on the complexity of the project. We also use a lot of, for instance, interviews of the scientists, so that whole fills a lot of space in the movie. Yeah. But I'm not counting the part of polishing the idea and understanding what the hell is it that we're talking about in every project, because every project requires us to understand a different thing. We do the human heart, we do combustion, we have done one for aeronautics. They study the aerodynamics around a plane in attack angles, something like that. But we have also worked for other departments here in the BSc that work in the life science domain, for instance, and they do research for about cancer, about diabetes, molecular dynamics, for drug discovery and things like that. And there's also another department that researches in earth sciences, and they do things about regarding climate and weather and things like that.
When it comes to communicating within the projects with the scientists that are your clients at this point, I assume.
Yes.
How do you find that different or more difficult or easier than communicating with commercial clients?
I don't think I have interacted a lot with commercial clients because I was protected by my producer.
and you're unprotected now, out in the open.
And I am unprotected, but it's not difficult. I mean, once they see the potential of, so once they see how it can look, if when you do these visualizations from the data, once you let's say show them a different way of visualizing things, most of them are really happy and excited about that. So they are very eager to participate. Also, in my experience, most of the researchers and scientists like to talk about their work, so that's not difficult for them to explain to you what it is about. So communication is fluent.
So within the project, I mean, the most grueling part in commercial projects for me were always the feedback iterations, where it was about the nitpickery about how this bunch of 3 pixels on a full HD image here has the wrong color. Do you have that in your current line of work as well?
I know. Yes, I remember that too. And no, I don't think it's the same. So we can have observations, but about the message or how we are. So what they are mostly concerned about is not the looks, but how we are conveying the science behind it.
Okay.
So if we are being rigorous or we are changing something that is not understandable in that way, things like that. So the iterations have more to do with the message than with the looks.
Is that an iteration at an earlier stage then?
We do a lot at early stages, but it might happen that once they see the final product, and this I think it happens in commercial work as well, that not every client has the same capacity or ability to foresee how it's going to look, right?
Yeah.
So that happens to us as well.
Let's jump a bit again with the topic. I'm sorry for it, but
Yeah.
When you're hiring or looking for new talent, what are you looking for, and what is maybe the top skills that folks need?
It depends. So my team is small, as I said. We are 2. The first one, I was looking for a Houdini animator, Houdini artist. So that was very clear. It had to have a proven experience in Houdini, and that's it. Because at the time it was, and I think it still is, quite difficult to find VFX or 3D artists that have a scientific background. There are some. I have known some people, who have changed especially from the scientific to the 3D part.
Okay.
And in some conference, I have found some people, a lot of biologists.
Yeah.
For some reason, that stopped being. Well, they don't stop being a biologist, but they don't work anymore as a biologist, and they work in making things like the ones we do, videos for explaining science and things like that. So that is one profile, VFX artist. But the next one we hired was an engineer, software engineer, because we wanted someone to help us to give us support in developing the tools that we need to communicate the scientific data to the VFX software.
And I assume that the VDB tools that you're developing is a direct consequence of that.
Yes, exactly, correct. Right. Exactly. So there is no one profile that we look for. Because it has to do with our needs at any moment. But also, I think this type of team and this type of work requires a multidisciplinary team, in the sense that you have an animator, so an artist, but also an engineer, maybe a scientist. Our boss, let's say, the team leader, is a physicist, so we also work with him a lot.
What am I forgetting here? What should I have asked you?
What else? Background check. Different types of simulation results from different fields. But that's kind of important. I don't know if I said it when I was explaining what data visualization is, but so one important thing, or one thing that I like especially about it, is that it's not tied to a particular field. The things that you learn in data visualization can be applied as general principles that you can apply to data or to information coming from different domains. So the things I apply in my daily work are this set of visual strategies for communicating with data, and I can do that for the transport of contaminants through the atmosphere, but also for this pumping heart or whatever else. So that's one thing I also like about this.
Universally applicable principles. In theory.
Right.
Cool. Well, thank you so much. That's
thank
been
you.
A brilliant insight into how you work and your daily work.
Thank you very much.
Thank you.